Hi everyone, we are going to go over key idea number 32. So the main idea here is enthalpy. And remember, enthalpy, or delta H, is the amount of heat absorbed or released during a chemical reaction. Specifically, the sign of delta H is going to mean a great deal for us. If we've got a negative delta H, then we know heat is being released, which tells us we've got an exothermic reaction. We're starting off high and ending low, and therefore releasing energy. However, if delta H is positive, we know that heat is going to be absorbed, and we're dealing with an endothermic reaction in which we start off low and end high. So this is a really important concept for us in chemistry because ultimately delta H is one of our driving forces. Specifically, we're looking for an exothermic reaction to promote a spontaneous or thermodynamically feasible reaction. So we're going to look at a bunch of different ways to determine delta H, but our way today is using calorimetry. So remember, calorimetry is looking at the heat exchange from hot to cold in order to figure out how many heat calories were released or joules were released by a sample. So typically, these calorimetry problems are going to examine a salt dissolving in water. So to kind of use my coffee cup calorimetry example and use that data to figure out a delta H, we're going to employ 3 steps. These are the same 3 steps that were outlined in the video. So I'm going to use these 3 steps as I read through the example and solve. So it says ammonium chloride is very soluble in water. I'm taking a mass of 4.50 grams of that ammonium chloride, and I am dissolving it in 50.00 grams of water. The temperature is going to go from 20.40 degrees Celsius to 15.20. So delta T here is T final minus T initial. Delta T is going to be 15.20 minus 20.40. We're going to get a negative here. We've clearly lost energy as it went from 20.4 to 15.20. So my delta T is going to be negative 5.2 degrees Celsius. It goes on to ask us to calculate the enthalpy of dissolution, or delta H, in kilojoules per mole. And we're told we can assume the specific heat of my solution is the same as water, which is 4.18 joules per gram degree Celsius. And it says the heat absorbed by the calorimeter is negligible. So first, in calorimetry, basically, a calorimeter is an isolated system. That means that matter or energy can't escape the system. So we've got 2 types of calorimeters. We've got a bomb calorimeter, in which you fill it with water, and inside of it you've got this reaction vessel that will be purged, so all the air will be sucked out of it, and it will be filled with oxygen plus some kind of sample that we're burning. And we'll combust that sample. Combustion is an exothermic reaction, so kilojoules will exit that reaction vessel and go to the water. We'll be able to use the temperature change of that water to figure out how many total Q, or heat energy units, were lost by that reaction. This is not what's happening here. This is a coffee cup calorimeter example. So imagine I'm using a styrofoam cup, pretty insulated. Over the top of that, I'll have some styrofoam or cardboard, and I'll put a thermometer down through that. In my coffee cup calorimeter, I've got the salt, the ammonium chloride, and the water mixed together. They're not separate. So when I'm trying to figure out how much heat energy that water absorbed or released, I know I'm going to use Q equals MC delta T, but the M here is going to be the mass of both my ammonium and my water because they're all in the same container. So my mass here is not going to be 50, it's not going to be 4.0, it's going to be 54.50 grams. I know my specific heat is 4.18 joules per gram degree Celsius, and I already calculated my change in temperature, which is negative 5.2 degrees Celsius. So I go ahead and I solve for Q, and my Q value is going to be negative 1184 joules. So what does that mean? Well, that means that my water lost 1,184 joules of energy. Well, how did the water lose energy if it's in this isolated system? Energy is not going outside of that cup. The energy is going into the salt to break that electrostatic attraction and dissolve the salt. So that means the Q for the salt is equal to positive 1184 joules. By the way, I would add that to my step here. B, I'm eventually going to take my joules and convert to kilojoules. I would add and flip the sign, because whatever happens to the water, the opposite is going to happen to the salt. And then I've got to get the proper units. I know my delta H has to be in kilojoules per mole. So my first step here is I'm going to go ahead and convert my joules to kilojoules. So I'm going to move that decimal point over 3 to the left. I'm going to get 1.184 kilojoules, but I still got to get it in kilojoules per mole. So I've got to take my 4.50 grams of my ammonium chloride and convert that to moles. So I'm going to do that using my gram formula mass. My gram formula mass is going to be 53.492, and I'm going to get 0.0841 moles. That is what I'm going to divide my kilojoules by. And when I do that, I get a final answer of 14.1 kilojoules per mole. That's my final answer. So what does this tell me? That tells me that if I were to dissolve 1 mole, or 53.492 grams of ammonium chloride in water, I am going to absorb 14.1 kilojoules per mole of energy. It's a little different than my Q. My Q is an extensive thing. It's dependent on how much of that salt I add to my water. So if I were to double the amount of salt here, I would double the amount of joules that were released by the water and absorbed by the salt. But my proportion in kilojoules per mole would be the same. If I doubled my moles, my kilojoules would double, so it would end up being that same ratio, or that same proportion. So to solve this, I'm doing 3 steps. I'm using MCAT to figure out how much energy the water absorbs or releases. I'm going to flip my sign because the salt does the opposite of whatever happens to the water, convert to kilojoules, and then I'm going to divide my kilojoules by the moles of reactants that I had.